All right, hello. We started talking about chemical reactions today, and we jumped right into balancing chemical equations. So I thought I'd make this little video so that you could write down some notes on the things we talked about during the demo where we burnt the magnesium, evidence of a chemical reaction, and what exactly a chemical reaction is. So what is a chemical reaction? Chemical reaction, very simply, is a chemical change where the molecules change their identity. Not the atoms. The atoms never change their identity, but the molecules, what's bonded to what, changes their identity. So new molecules are formed by breaking chemical bonds and making new ones. So real quick, I'll demonstrate that on my little whiteboard here. So imagine if you had two chemicals that were coming at you or coming towards each other, really is what we're talking about here, right? They have to bump into each other in order for a chemical reaction to happen. And when they do, when they bump into each other, let's see if I can sketch this quickly. When they bump into each other, the bonds between the atoms break and new bonds are formed. So a bond can form between these two atoms, and this bond right here would break, right? So what you would end up with instead, as these things bounce away from each other after hitting each other, you would have something like this and something like this. So you see, we're not actually changing the identity of the atoms. We're only changing who they're bonded to. All right, so I just wanted to take a moment also and tell you something about John Dalton. He's one of my favorite people in chemistry. Um, John Dalton, sorry, there we go. John Dalton is one of the fathers of modern chemistry, along with Antoine Lavoisier and Marie-Anne Lavoisier, who's always overlooked. And John Dalton is the first person who proposed a unified theory, and that's theory with a capital T. Remember, we talked about theories are facts that have been proven, and they incorporate big ideas that explain a lot of things. He was actually a high school chemistry teacher, and he was reading all kinds of stuff from other people's work, and he put it together and said, look, I think this is what's happening here. So the first atomic big T theory was from John Dalton. That was back in the 1800s, early 1800s. So how do we know if a chemical change is happening? There's evidence, and so there's several different kinds of evidence that tell you if a chemical change is happening. First one is light and heat. So candle burning, light and heat, there you go, right? Glow sticks make light. And light is actually one of those really interesting things because not very many reactions actually make light. So, things, combustion, burning things makes light. And the luminol reaction makes light. But most other reactions don't. So if you see light happening, it's probably true. Not a light bulb, though. Light bulbs are not a true chemical reaction. If heat is released, like when we burnt the magnesium or a hand warmer, and it could be released and make the surroundings hot, or it could be absorbed, which makes the surroundings cold, right? So if a reaction releases heat, if these molecules release heat from those bonds, then the surroundings would get hot and the thermometer would be, the temperature would go up. If they absorb heat from their surroundings, then it would seem to get cold. A gas is evolved. Gas is being evolved is a fancy way, that's the chemistry way of saying bubbles formed. So when we did our 3-bottle problem and you mix the two chemicals and it made bubbles, that is a gas being evolved. A precipitate is produced. Precipitate, remember, is the cloudy stuff. And we saw this too when we did our 3-bottle problem. Now, it wasn't orange, it was white. So it could be any color. But what happens is that a clear solution will become cloudy, and that's called a precipitate. It's actually a solid particle or particles that are forming inside the aqueous phase. Some key words from this afternoon. So some more evidence of a chemical reaction. If it changes color, that's a chemical reaction, or odor. And we're not just talking about bad odors like skunk odors, but actually if we have good odors as well. Chemists live for their smells and all kinds of other things as well. Now, a couple of things I want to, or one thing that I really want to make sure that I'm pointing out here, just because something gets hot or cold, or just because it changes color, does not necessarily mean that there's a reaction happening. We have to be very careful to know something about what we're studying, because sometimes it's actually just a physical change instead of a chemical change. So here's some examples of things that are not real reactions, right? These are physical changes, not chemical changes. So boiling, right? Boiling water, it gets hot because you put a flame under it or you put it on the stove. That is not a reaction. Same thing with ice melting. Any phase change is a physical change. The chemical is still the same chemical that it was before the phase change. Dissolving things in water, making them an aqueous phase, like Kool-Aid, like salt water, that is not a chemical change. Those are physical changes. NaCl, table salt, is still NaCl when it goes from a solid to the aqueous phase. And light bulbs. Light bulbs are not a real reaction. What's happening on a light bulb, modern light bulbs are LEDs, and that is actually light that is emitted from electrons moving through a semiconductor. Older light bulbs, which you may still have in your house, incandescent light bulbs, actually get hot, and they get so hot that they glow, and that's what makes the light. Those are not true chemical reactions. Nothing is changing its chemical identity. So let's talk for a minute about two new vocabulary words: spontaneous versus non-spontaneous. Spontaneous reactions happen on their own without our help, without help from a scientist, is what it says back there. So as soon as two chemicals come into contact with each other, they react. And that could be fast or it could be slow. So if you have two things that explode when they meet, you pour the two things in there and boom, there's a spontaneous reaction. Another spontaneous reaction would be actually a car rusting out sitting in your backyard. Metal doesn't need any help to rust. So that would both be spontaneous reactions. Non-spontaneous reactions, they go only if you give them some energy first. So you have to provide them with heat, or you have to provide them with a shock. Sometimes there are chemicals that are touch sensitive, and if you touch them and you give them a little energy, they will actually react. That is different from the rate of reaction. So spontaneous versus non-spontaneous does not tell you how fast the reaction goes. Just like the car rusting out, that is a spontaneous reaction, but it's going slow. And there are some spontaneous reactions that go slow and some that go fast. There are some non-spontaneous reactions that go slow, and there are some that go fast. So the speed that the reaction goes is not related to whether or not it's spontaneous. The last thing I want to talk about here is equilibrium. When you think about reaction, you think about reactants becoming products, right? And usually we think about, we have some reactants. Oh, that's backwards on there. Oh, sorry. We think about having reactants, and the reactants eventually go away and they're gone. And all we have left is products. But some chemical reactions don't go all the way. When you start to make the products of the reaction, the backwards reaction starts to happen too, and some of the products become reactants. So instead of just having a one-way arrow, we actually have a two-way arrow. This is like a reversible reaction. Now, if that reversible reaction eventually reaches equilibrium, what that means is that the forward reaction is equal to the backward reaction. And actually, the way that we draw that, when we draw equilibrium arrows, we draw them as little half arrows, right? So it's an arrow, but the arrowhead is only a half arrow. And that tells you that we're talking about reversible reactions that are at equilibrium. And again, I'm sorry that that's backwards on there, but I'm an old person using technology, so you'll have to forgive me. The reaction doesn't stop just because it gets to a point where the backwards and the forward reactions are going at the same rate. It's still going. It's just that they have reached what we call equilibrium. Here's a quick little graph to show you. When you start off with reactants, over time, the amount of reactants goes down because you're using them up. And the amount of products starts off at 0 and it goes up because you're making products. Whoop. When you start having an equilibrium reaction, what happens is instead of this line for reactants coming down all the way to 0 and getting all used up, and this line for products going all the way up and then stopping because that's the end of the reaction. What happens is they reach this flat part of a graph where the reaction is at equilibrium and the amount of the reactants that's being formed and the amount of the products that are being formed stays constant. So you get to a point where the reaction seems like it has stopped, even though it really hasn't. And so it's going backwards and it's going forwards and they're going back and forth at the same speed. And so the amount of the reactants and the amount of the products that you have at equilibrium becomes constant. So you're going to see graphs like this as we go forward in the year. We're going to talk about it over and over and over again. This is going to be one of those big ideas in chemistry that we talk about. And that's it. Thanks for watching.